I'm going to start off today's recording by giving you a preview of some of the amazing things that you're going to be able to tackle in higher levels of mathematics with some of the tools that you have today. And don't worry, this isn't a class that's going to be simply about like you need to learn this for the future when it finally becomes useful. We're going to find plenty of ways that it's going to become useful for you, both in terms of expanding your awareness of different functions today, as well as just kind of some fun logic puzzles. But also I want to kind of show you that the things you are learning right now are incredibly powerful. So this is a fun little example here. So look here at somebody who's trying to model this vase. And you can see that there's a bunch of different points that you can plot around this. And in fact, the same software works very commonly if you're into something like Photoshop or most of your picture editors, where you can grab faces, right? Or you can crop out different objects by just kind of clicking on them and having it select things and pull it out. As it's mapping surfaces with polynomials, it's trying to guess at exactly what it is that you are looking for, and it's putting a bunch of little dots around it, and then it's connecting those with a nice smooth curve. So like, for example, here, like you can see that there are, I don't know how many dots here, 1, 2, 3, 4, 5, 6, 7, about 14 dots here. And so right now I'm looking at trying to model all this with a degree of best fit polynomial equal to 1. So that let's clarify what that is. I'm making a polynomial whose degree is equal to 1. That might feel a little weird. Let me pull over there notes for a moment, just so we can have something to write on as we get our thoughts organized here. So if we pull out, let's pull out our pen. And if we think about what polynomials are, remember that a polynomial was something where it was like this function, and it was a pretty simple function. It's so that we were going to have some kind of number, some kind of first number. This is what we call our constant. So we write it as like an a sub 0. This is kind of like our no x's object here. And then we could add this to some kind of other number, which we'll call our first coefficient, and that goes along with an x to the first power. You can start to see that we've kind of got like our first coefficient, our a1, goes along with our x to the 1 power here, and our a0 has no x's next to it. So it's a nice little convention to kind of say, what do we have here? We have a constant plus some kind of amount of x's, and you can write that in as amount of x's. And then we could add that into some other term where we're going to have some second number that goes in front times x to the second. So that's this a2 is really our amount of x squares. So we can even write that in. We could write this as a2 amount of x squares. And you can even write it in over here if you wanted. This would be like there's a1 of these x's, a1 of these x's, and our constant is just kind of the thing that stays still. So this is like our a0 constant. So it's like we got a number. These are just numbers. These are numbers that aren't changing. This is a number, and this is a number of x's, and this is a number of x squares, and we could keep going like this as far as we want, as long as we're just simply doing multiplication and addition and subtraction here between our numbers and our variables. Then this is going to classify itself as a polynomial. Okay, so what would it possibly mean if we said that we had something back over to our mapping where this was a degree of best fit polynomial equal to 1. Well, the best fit part probably is it trying to get between all of those dots in a good way. The degree equals to 1. Let's go back over here and take a look. What would it be a degree equals 1? Well, we probably guess that that's going to be when I have like this one right here, where I have a highest power equal to 1, because obviously we could have higher powers than that. We could keep going forever. And so we could take a little moment and kind of pull this off to the side and do some analysis and say, what would that be if I had a number plus an amount of x's, and that's all I had in my function? Well, we might look at that for a while and say that looks kind of similar to us. Maybe that looks like this. We could call this b, and we could call this m times x equals y, and we could rearrange this a little bit to say mx plus b equals y. Oh, so this is just a straight line. This is just a line. Okay, so a polynomial with degree 1 is just our typical line. And that would make sense because, again, as we go back over here to our picture, notice that the way it's mapping it is just with a straight line. And maybe it's easiest to see this as we start to kind of increase the degrees, because after we go to a line, I think the next one would be if I had, instead of x to the first, it'd be x to the second. That'd be a parabola. Let's see what happens. Oh, and sure enough, we kind of see this curve. It's like a parabola, and we can even see over here in the dots, it's like trying to get through all the dots, but it's doing a horrible job of it because it's just a parabola. And we could say, okay, well, what about raising it to a third power? This would be where we could go all the way up to using cubics. Oh, not much better. Fourth degree power? That's interesting. Notice what just kind of happened here. We went from something that maybe wasn't doing much better to now this thing that has 1, 2, 3 kind of humps in it. Okay, let's see what happens if I add in another amount here. Oh, not much of a big change. 6, ooh, interesting. 6 has 1, 2, 3, 4, and 5 kind of humps in it. Maybe there's a pattern there. Maybe there's the degree is going down by one number, and we're starting to kind of like fit in here better. Let's see what happens if we start raising this more and more and more. And we start to get something that just fits very nicely into our curve. And in fact, it fits perfectly through these 14 or so points when we have a degree that goes up to 14. So it's almost like we could always be making this thing better and better and better by just allowing ourselves to play with higher and higher polynomials. Now that's really interesting because being able to map data accurately is something that's useful in a variety of fields. But what's really interesting for further mathematics is sometimes in the higher level classes, we like to say, okay, well, what can we now do? How can we transform these into different ideas? And so as a preview for something that happens all the way up into calculus, you get into this idea of rotations. And I think that that's just an absolutely beautiful graph. Watch it as it kind of turns all the way around. And you can really get a nice computer model that occurs as a result of playing around with these polynomials. Now, this is something that exactly the inner workings here are beyond the scope of this class, but they're not too far above where you are at currently. Let's think we've got pre-calculus above this class, and then calculus above this class, and then we've got calculus 2, and that's really where this comes in. So you're only about 3 semesters if you studied well and passed all the math courses. In less than 2 years, you would be learning about stuff just like this. So the things that you're playing around with really do come back into some powerful, powerful ways. Okay, interesting. So that was a fun little aside. So let's talk again. What are polynomials? Polynomials are these things where I have a number, an amount of what I like to refer to as kind of shapes. These x cubes could be thought of as shapes. These are cubes, and squares are shapes, and these are just my little unit blocks we've been playing around with before. This would be 1/6 of a unit block. And even though I have the square root of 3 here, and square root of 3 is a crazy number, it's still just an amount. It's an amount of cubes, so that works out perfectly fine. Well, I'm going to let you take for a moment here what the degree of this polynomial is, do you think? And I'll go through a couple of these other ones and leave the last one for you as an example. But let's see. So we've got the degree here would probably be, just like when we did it in our tool over there, it'd be a degree of 3. Because that was kind of the high power, how powerful, how complicated we were allowing this model to be. Okay, what about the leading coefficient? Well, what's leading? Leading would probably be, probably not just the thing in front, because we could always move these around, but it's going to be the thing that's attached to the degree. So this is going to be one of the most powerful numbers in this model. So the leading coefficient here would actually be root 3. Now notice, again, even though up here I drew this where I had the constant in front, I can always rearrange things so that I have constants in front or any term in front, but our leading coefficient is more about what's the thing that's leading this model. And the thing leading the model is going to be the most powerful number, the one that's attached to the most powerful variable here. Okay. Now, what about the constant coefficient? What's our constant? What's not changing? Well, again, we can think about this entire thing as being nothing more than a story. I'm asking questions of x, and I say, what happens if x equals 1? What happens if x equals -1? What happens if x equals 5 billion? And we could say, okay, well, our first term is going to change a lot depending on what x has. In fact, it's going to change so much because of that cube. That's why it's so powerful. The next term is definitely going to change. So that would be silly to call that thing constant if it's changing, but we're always going to be subtracting 1/6 at the end. So that's interesting. That's probably going to be our constant, is just this 1/6, but actually it's a -1/6, right? Because it's actually like we have, instead of minus 2x squared, it's like we have a plus of a negative 2x squared, and instead of a minus 1/6, it's like plus a -1/6. So we like to think of these negatives as being the amount or part of the amount that corresponds with the numbers. Now I've got this one here marked off as an NA, and the reason I have it marked off as an NA is because I'm trying to give you a hint that this one is not a polynomial. And I'm going to leave this to you to figure out why. Look through the polynomial, see if there's anything interesting. I'll give you one hint. Polynomials are always going to be nice, smooth curves where there are no problems. There are no asymptotes that are caused by dividing by 0. There are no restrictions on the domain like you might have if you were doing a square root of a variable. It's going to be a nice, smooth curve. This one here doesn't work that way. So see if you can figure out why that is. Okay, and I'm going to leave this one for you too. I'll give you a hint though. This one is in fact a polynomial. So even though I've said before that you need to sometimes be a little cautious of dividing by things inside a polynomial, it's important that we not forget that I don't just say things. We're a little more clear than just things. Dividing by a number just changes the quantity of my x's and my x squares and my x to the fourth, and I'm allowed to change quantities of these all I want. I just need to make sure that I don't ever have any troubles where if I put in certain x values, I might not get a nice smooth curve or a nice clean answer. Okay, so that's for you to kind of recall a little bit. Pause the video if you'd like before you move on. But I'm going to show you here, again, just a little bit of a preview of something kind of looking like what we saw in the last one. So let's take a look here at y equals x, or what we call f of x equals x. And if we graph this, again, this is nothing more than our line, because we could think of this as like an mx plus b. But we might need to look at the numbers here as being how many x's do I have? If m times x equals x, that would make m equal to 1. So it's like I have one x plus, and then there's nothing at the end, so we'll put nothing at the end. So it's like I have a slope of 1 and an intercept of 0, and that makes total sense with my picture. This parabola we've seen plenty of times, so we're not going to review on that one. The cubic is one that we've seen pretty often, but notice that there's starting to be a pattern that emerges. I mean, after all, doesn't this one kind of go up towards the positive as we go to the right and down towards the negative? And this one here seems to go to the positive either direction, because if I take either negatives times negatives or positives times positives for my squaring action, that's going to work out to be a growing towards the positive kind of answer either way. But here again, I see something that maybe goes up to the positive and goes down to the negative. That's interesting. And then this one here goes up again to the positive to the positive. And this one here again to the positive and to the negative. I wonder why that is. That's an interesting pattern at the very least. So let's think about that. Why do we have that? Well, if you think about some of the numbers we could put into x squared, like if we say what happens at 2, you would say, well, 2 squared would be 4, and we'd go up to 4, and we'd plot a point. And we'd say, what about negative 2? And I'd say negative 2 times negative 2 would be a positive 4. We'd go up, we'd plot a point. But in my odd numbered powers, I would be saying, what is negative 2 times negative 2, which would be a positive, and then times negative 2, which is back to the negative. So it's almost like the negatives here now kind of go back to their negative state, which is why we have such big drop-offs that happen on the left. But again, with the x to the fourth, that's an even amount of multiplying things. So whether you're a positive or a negative, you're going to end up being positive. So that's going to arc upwards as we ask different questions. But if I go back to the odd, I flip back to that idea of saying if I have negative times itself enough times, then I retain, I kind of go back to that negative state if I started there, but the positives will keep growing. So there's a little bit of a pattern here. Like, just keep this one in the back of our mind. This one's going to come up as a nice, useful aid for us. Okay. Now, before we go too much further, I want to ask us one of the scariest looking problems that we could in this entire thing as a way of preparing to say, if we can do this, I'm pretty sure we can do anything. Now, we're going to try to sketch a somewhat decent graph of this following. So, first of all, that looks intimidating. That looks incredibly scary. And it's important that if you are looking at some problems like this in math, that this give you an emotional reaction. It's okay that it does. Like, we are all humans. Math is not a logical sport. It does, in fact, have quite a lot of emotional triggers that are in that, and this is one of those. This one is intimidating. I mean, you had x minus 4 to the 33rd power. I mean, that's just ginormous. And then if that wasn't bad enough, you got x minus 1 to the 198th. I mean, what are we even supposed to do with that? Well, obviously, we could always throw it into a calculator. The calculator kind of carry it for us, but maybe there's some kind of pattern here. Maybe there's something happening behind the scenes that if we could see it, we might learn a little something. And that's kind of what I'm thinking of here. Maybe there's something to be discovered here. So an important thing in math, and especially if you're on a test, is not to worry about getting things right. Getting things right is a byproduct. It's the result of doing many other things. The most important of which is just to have fun and play, just to try some things, see what they get you, and to kind of adjust and be strategic about it from there. So let's just do one and only one thing. I mean, let's pick something basic. At the very least, we know we're gonna have to graph. So let's put down a nice sketch here. So I'm gonna at least draw in a coordinate plane. And that's a pretty big step. I mean, that helps us to frame our thoughts. We're getting our eyes involved. And now we kind of take a sit back and we think through this one. And we say, well, there's a lot of questions I could ask. There's a lot of numbers I could ask. But there should be some things that kind of pop out. Like, it's not every number in the world that might be drawing our attention. There might be something here that's drawing our attention. Like, at the very least, I see these numbers here, this 4, this -1, -4, the -1, the +1, the +3, the +4. And it makes me kind of wonder, like, what's going to happen if I plug in a 4? Like, let's try that. Let's let this entire thing be f of x so that we can keep our work nice and organized. And let's just play. Like, let's just see what happens if I put in 4. Well, okay, let's play around. That's going to be 4 minus 4 to the 33rd equals, well, that's going to be 0. And then we're going to be multiplying that by a bunch of stuff. In fact, actually, now that I think about that, if I just have 0 times a bunch of stuff, I don't have to do anything else. 0 times a bunch of stuff is just going to become 0. Like, I could plug this all out if I wanted. This would be 4 minus 1 to the 198th times 4 plus 1 to the 5th times 4 plus 3 to the 3rd times 4 plus 4 to the 2nd. And I could go through all this power, but I mean, this is 0. Everything else, like, what, 3 to the 198th? Why do I care about what that is? I'm about to multiply it by 0. And what about the next thing? That's going to be 4 times, that's going to be 5 to the 5th. Why would I go through multiplying all that? It's about to be 0. In fact, it's all going to be 0. Why am I even spending time on it? Let's make that 0. So it says that if I ask the question of 1, 2, 3, 4, if I ask the question of 4, I get a height of 0. We'll plot the point. And we have our very first point plotted down. Now, we are making wonderful progress. We've already begun sketching our graph. We've got some familiarity with the functions. Well, from here, we should begin to notice that I think we're going to be able to find even more zeros, even more of these zeros that pop out. After all, isn't it going to be 1 if f of, like, 1? Like, isn't that going to be where I plug in 1 here and I get 1 minus 1? I'm going to plug in 1 everywhere, but here in particular, it's going to be a 0, and that's going to zero everything out. So that's interesting. F of 1 gets me 0, so I can plot something right there. At 1 comma 0, that's another 0. And I think there's going to be even more. There's going to be at f of -1, it's going to be a 0, and at f of -3, it's going to be a 0, and at f of 4, it's going to be 0. And there you have it. We've already got a bunch of points to put on our graph. At 1, we have it. Let's see, at -1, we have it. At -3 to -3, we have a 0. Negative, or positive 4? -4. -4. We're going to need to plug in a -4. And so that would be another 0. Okay, well, we've got plenty of points now. Now, this might be recalling if we've played around with graphing curves before and trying to find out where all the zeros are and doing test points. That might come into play here. That's a technique you could think of. But there's also a little bit of something to be said for, what if we were to just kind of do a little bit of a logic puzzle? Like, I like to think in extremes. I like to think if we're going to take a situation and it's going to be something crazy, let's make it crazy. Let's look at the big, scary, hairy problem first. And so I'm curious about what happens if I put in a number that's way, way big positive. Like, let's put in something like 10, I don't know, 10,000. Like, let's put in something huge and just play around with that. Why not? Okay, well, if I put in something that is 10,000, then at the very beginning, I've got 10,000 minus 4. And so that's going to be just about 10,000. So I've got something here that's going to be, I don't know, about 10,000. And it looks like I'm going to be raising it to the 33rd power. I probably shouldn't put the little dash there. That was supposed to be an approximate, but it almost looks like a negative, so I'll take it away. So it's about, I'll do a squiggly equals, about equal to 10,000 to the 33rd. And then I've got 10,000 minus 1. Well, it's just about 10,000. So that's going to be 10,000 to the 198th. And the next thing's going to be about 10,000. The next thing's going to be about 10,000. They're positive numbers all the way down. And so it looks like I'm just going to get a huge, huge number. This next thing's going to be some positive, and the next thing's going to be some positive, and the next thing's going to be some positive, and that's going to get me just something huge. So as I go up to 10,000, this is going to get really, really big. So that means that my graph is kind of going to grow. It's going to grow out this way. Okay, well, that's an important thing. Now I'm able to get some things on here on my graph. Well, what about if I was to plug in things that were way to the negative? I'll have to be a little bit more careful on here, because if I plug in now negative 10,000 and I put it in here, it's going to be negative 10,000 to the 33rd, and negative 10,000 to the 198th, and negative 10,000 to the 5th. So let's draw that in. Negative 10,000 to the 5th. And then negative 10,000 to the 3rd, and then negative 10,000 to the 2nd power. Okay. I'm feeling like we're doing a lot of erasing. Maybe we should write down some work. Let's do f of, we did 10,000 first. F of 10,000 we said was pretty close to equal to 10,000, you know, to the 5th, no, to the 33rd, times ... and that just got us something that was positive, something very, very big. So we'll put greater than 0 for sure. Now we're doing to the negative 10,000. Maybe we'll be a little bit more careful. F to the negative 10,000 will be approximately equal to negative 10,000 to the 33rd times negative 10,000 to the 198th times negative 10,000 to the 5th times negative 10,000 to the 3rd times negative 10,000 to the 2nd. Okay, what does this end up getting us? Well, the important thing to pay attention to is we already know it's going to be huge. It's going to be absolutely massive, but I'm curious if it's going to be massive positive or massive negative. I mean, here I've got to the 33rd power, and so let's think about this. If I have something and I square it, just like we were talking about before, if I multiply it twice, negative times negative gets me a positive, okay. But if I do it 3 times, I go back to negative. And if I do it 4 times, I go back to positive. So it's on the evens that I'm going to get a positive result. It's on the odds that I'm going to get a negative result. So this 33 is an odd power, so I can say that that entire thing is going to turn out to be negative. Okay. Well, under the same idea, the next 198, that one's positive, or that's an even, so that's going to make everything multiply out enough times that they kind of cancel each other out. The negative times negative is a positive, that's an even, times negative is an odd, times a negative is an even, so whenever I'm on my evens, I get these positives. The next one's going to be odd, so I can multiply that by a negative. And then the next one there is going to also be odd. It's going to be another negative, and the one at the very end is going to be a positive. So I've got negative times positive times negative times positive. I believe if you multiply all that together, you should get a negative. Now, how would we write this so that we keep track of it properly with mathematics? Well, we could write something like f of negative 10,000, and we could just say is going to be less than 0. Right, we don't know exactly how big it is, we just know it's going to be negative. And we'll put it up here in our picture, negative, and we got something that's going to be coming down like this. Well, so far so good. Okay, let's think what else we have. Could we choose some test points? Could we choose exactly what's going to happen, like between the negative 4 and the negative 3? Like, could we do something with f of, I don't know, negative 3.5 and plug that in? Okay, well, let's try it. Why not? This one is going to be a little bit more manageable, so we should probably plug it in exactly. This would be, let's see, 3.5, negative 3.5 minus 4 to the 33rd, and then we have negative 3.5 minus 1 to the 198th, and then negative 3.5 plus 1 to the 5th, and then negative 3.5 times, let's see, instead of plus, we could do plus 3, plus 3. Plus 3 to the 3rd, and negative 3.5 to the plus 4 to the 2nd. Okay, so let's go through here and find our negatives. We got a negative minus a negative is going to be in, or negative minus a number is going to be still be negative. So we got negative to an odd power would be negative. Okay. Next one would be a negative number to an even power would be positive. And then I've got negative 3.5 plus 1 to be a negative number to an odd power would be negative. And then here I've got negative 3.5 plus 3. That would be negative number. And then to an odd power would still be negative. And then over here I've got negative 3.5 plus 4 would be a positive 0.5 to a positive power would be positive. Okay. So what does this get us all in all? This is negative times positive times negative times negative times positive. So again, this is going to be something that is negative. And we could write that in here. The f of negative 3.5 is something that is going to be negative. So we'll put that in right here. This is actually going to be a negative value right in here. And we could keep going through all of this. But I bet you there's an even faster way. Let's take a look. So let's see. What about this in between the negative 3 and the negative 1? Okay, well, between the negative 3 and the negative 1, that's going to be, let's see, how's that going to change anything? I'll tell you what, let's do a couple more data points. We'll play around. Between the negative 3 and negative 1, let's choose another test value. Let's do f of negative 2. F of negative 2 is going to be what? Negative 2 minus 4 is going to be negative. To the odd power is going to be negative. Okay, so we're going to go ahead and write that in. We'll say that this is going to be a negative. Negative 2 minus 1 to an even power is going to be positive. Negative to the, let's see, negative 2 plus 1 to an odd power is going to be negative. Negative 2 plus 3 is going to be positive. To an odd power is going to be positive. And then negative 2 plus 4 to an even power is going to be positive. Okay, so that's going to get us, let's see, negative times positive times negative times positive is going to get us a positive now. Okay, so then we switch over to the positive. Oh, now I start to see the pattern that it was kind of tickling my brain. Take a look at this. I'm starting to see some places that we could go a little faster. Take a look at this one here. This one here, this little plus sign, goes along with our second power. But isn't that always going to be positive? Like, isn't anything I put in that parenthesis going to be positive? Like, I'm raising it to a second power. It has to be positive. And sure enough, it's positive down here. It's positive down here. And any other number I would put in there would be positive. Well, in that case, let's think of the other ones. In fact, this even one right here, even degree, is also going to be positive. We're raising something to 198th is always positive. So that one's always going to be positive. That one's always going to be positive. Okay, that makes things easy. And then what else are we doing? Well, we had it where it was negative and negative and negative, okay, and then it was still negative and negative and negative, and then it became negative and positive. Do you see here? This one here switched over. Okay, maybe we'll do one more and see what happens at the next test point. We're going to be looking at something between negative 1 and 1, so let's plug it in. F of negative 1, between negative 1 and 1, 0 would be a good option. So let's put that in. So now I'm going to be doing 0 minus 4 to the 33rd power. And then 0 minus 1 to the 198th power. Oh, but I already know that that's going to be positive. And then I've got 0 plus 1 to the 5th. And then 0 plus 3 to the 3rd. And then 0 plus 4 to the 2nd. Equals, let's see, okay, so it's going to be a negative here to an odd power will be negative. A negative to an even power, we already knew that was going to be positive, and actually this one was going to be positive as well because it's another even power. This next one, the 0 plus 1, is going to be 1 to the 5th. That's going to be a positive value. And then 0 plus 3 to the 3rd, that's a positive to a 3rd power. That's a positive value. So now I've got negative times positive times positive times positive times positive is going to get us a negative. Okay, so that means that f of 0 is actually going to be less than 0. It's going to be negative. We'll put that in over here. So that means I've got kind of a negative that's happening in my picture right down here. But do you start to see the pattern? Look right here. Maybe it's these positive signs are starting to take over. Look, there's one here now, and there's one here now, and there's one here now, and there's one here now. I wonder when this one here is gonna flip over. Well, it would need to flip over when I was plugging in x values that were bigger than 4. Well, actually, doesn't that make sense? Because isn't that what we were doing when we plugged in our positive 10,000? Is when we plugged in our positive 10,000. This is when we said that we were going to have a positive result times a positive result. We had positives that were going all the way down the line. Okay, so let's see what's going to happen at this between 1 and 4. Between 1 and 4, are any of these going to change? Or can I cut out some time? Like I could say at f of between positive 1 and 4, let's choose, I don't know, f of 2. Like isn't f of 2 going to be where this first parenthesis is still negative? And then everything after that is going to be positive because the things in the parentheses are at least going to be into the realm of positive. So like, again, I've got a negative happening here. So we can go up to our picture and we can say, okay, well, then that means I'm going to have a negative between here. And we already know that after 4, we get a positive. So I think we have enough to get a pretty decent sketch now. Let's go and take a look. So we're going to have something that kind of swoops in, and it's got to cross right here at this 0. It has to touch that 0. That's a point that we figured out earlier. But I can't bring it up into the positive because it says it's negative right after that. So I guess I got to kind of like dip back down a little bit. So we'll dip down, and then I got to come up and I got to touch the line. I got to touch at this 0 right here. This x equals -3. My height was 0. And then I'm going to go up into the positive realm for a bit. We can see that. So I'm going to dip up in the positive, and then I've got to come and touch this 0 here, and then I'm going to be in the negative for a while. And then I'm going to touch this 0 right here, but then I got to stay in the negative. That's what we found out, stay in the negative down here. And then I've got to cross this 0, and then we're going to go all the way up because we had discovered that before. And that's a pretty decent sketch of what we're playing around with. Like, as far as only having, I don't know, a handful of points to play with, that looks pretty good. Something kind of swoops up, dips back down, comes back up. Interesting. Let's check in with the computer system and see how well we did. Now I'm over here in Geogebra, and I tried to graph exactly what we had over here, and it's a really interesting problem that I ran into, because what you can see is going across over here on the x-axis, we got our normal numbers, the -8, -6, -4, etc. But over here in this vertical axis, we start to see something crazy. So this 5e8 is computer language. It's a shortened way of saying that this is 5 with 8 zeros after it. Right? So 8 zeros, that means that we're talking about 500 million. And the reason it's so big is because I've been playing around with the scale here, and I keep trying to make it bigger and bigger. I keep trying to make this scale where, I don't know, maybe it goes down to negative, I don't know, 8 billion. That'd be 3, and 3 more zeros. And then I'll put over here that I want this one to go up to 8 billion, 8 with 9 zeros after it, 3, 4, 5, 6, 7, 8, 9. And if I press enter, you can see I really I can't get high enough on this graph. It just grows way too quickly. So the computer system actually can't graph what I'm trying to verify. But we can see kind of the exact same behaviors we had before. You can see that it goes really, really far down over here as we go a little bit to the negative, and it crosses at -3, and then it seems to dip up, and then somewhere really high that I can't seem to reach, it's going to turn around, it's going to come down this way, and it's going to loop back up and just kind of barely touch before going back down and then coming back up. So it's kind of got this dip where it's going straight down on the left hand side, and we'll go back over our picture. See, it's going down on the left hand side, and then it's kind of got this little bit of a dip that's happening between -4 and 3, right? So like I can't get it high enough. It's absolutely crazy. Let me actually, so I was just playing around with the graphing system, and I actually ended up working it to the place that it actually ended up just failing on me. So you can see that there are some times that even with these crazy hard problems, like the computer systems fail us as well. And you can try graphing it if you like, but I have a feeling it's going to be quite a lot for your calculator to handle. But nonetheless, we know exactly what it's going to do here. We know where those zeros are going to be. We know what the behavior in between is. We can use our test points. We can use our logic, and we can even use patterns to make this go a lot quicker. Now, one other pattern that I want to point out while we're here is to take a look at kind of what's happening with these multiplicities, as they're called. So the multiplicities are the number that's happening up in the exponent. So let's take a look at this 33 here that's happening. Actually, let's erase this one, and let's deal with just let's take away all of this, and we'll go back to just the original problem. Let's take a look here at what's happening. This x minus 4 to the 33rd power. Now, we knew that was going to be an odd number of an exponent. And remember, when we were looking at our third powered graphs and our fifth power graphs up here, that those odd numbers kind of had this S shape, this kind of, I don't know, going one direction, then going the other direction thing. Let's take a look down here at this 0. The 0 here that corresponded with it was x equals 4, and so that's over here. And you'll notice that it's a place where we cross over from the negative into the positive. Interesting. Okay, let's take a look here at this x. This 0 here was when x is equal to 1. So let's look over here at the 1, and when it hits the 1, you'll notice it doesn't cross over. It actually just kind of touches and dips back. Do we think that pattern works for all of them? Like, let's take a look at here. This x plus 1. This x plus 1 had the 0 of x is a negative 1, and it's got an odd multiplicity, so maybe that's a crossover that happens there. And sure enough, right here at this 0 at x equals negative 1, it crosses over. And then here's a 0 at x equals negative 3, and it's going to be an odd power. And oh, sure enough, it crosses over there. And then this one should be an even power, so it should just kind of touch and dip back down. Oh, and it does that too. So at all of these zeros, we almost have this behavior of like, do you touch and then go back the way you were headed? Or do you touch and cross over? And on a very small scale, it seems to match up with like what we were doing up here, is that the even numbers are where I'm just kind of touching and then I'm dipping back up, and the odd numbers are where I'm crossing over. And I think that's probably because, just like with the exponents, those are the times where when we were plugging in our values, they caused one of these signs to flip over. I mean, after all, this one was always going to be just doing nothing to the overall sign. If it was negative before and the number flipped inside the parentheses, it was still going to, like, if let me clarify, if the entire result was a negative before, and then we were able to change just the inside of this parentheses, it didn't have an effect because it just stayed positive and was always positive and will be always positive. And so we really only switched the sign of the graph when we changed one of these odd powers from one sign to the other. Like, for example, when this one flipped over from negative to positive, we went from the entire graph going negative to positive. Kind of interesting. The other ones don't actually matter. So lots of patterns to be had in these polynomials. Very interesting. Okay, so let's use the end behavior of these graphs to determine whether the degree is even or odd, and we'll determine if the leading coefficient is positive or negative. Like, let's see if we can actually apply in some of these patterns that we've used, and we'll start to classify these things without even needing to know points, just by looking at them and discovering our patterns. Well, for example, take a look here. This one started off in the positive direction, and then it ends up in the negative direction. So we've got to think to ourselves, is it going to touch? Like, it's switching direction over the long run. And if it was an even number, just like if we go back up to our references, if it was an even numbered exponent, we would expect it to have the same end behavior to the left or to the right. It'd either be both going up or possibly both going down if we wanted to make it negative and do a full flip. But we only have that opposite action when we're dealing with an odd power. Okay, so let's go here, and we're kind of classified now that something, regardless of what's all being multiplied in here, has to be an odd power. And in fact, we can even see that if we look in at this graph. Like, here's a 0 where we cross over. So this must be something that is an odd multiplicity. This is an x, I don't know, plus something. Maybe that's a 4, a negative 4 down there. So there may be x plus 4, because when we plug in negative 4, that's a 0. But it's crossing over, so it's going to be some kind of odd exponent. Interesting. And over here, this is where something's just kind of touching and dipping back. So this is going to be a 0 to an even exponent. Maybe this is something like, I don't know, x minus 2 to the even, some kind of even power up here. And so we could think to ourselves, well, okay, I've got an odd power in my exponents. I've got an even power in my exponents. After we do lots of foiling, we're going to have a leading degree over here that is x to an odd. And over here, we're going to have a leading degree that is x to the even. Okay, so that kind of helps us to see that maybe what we're playing around with is something where it's x plus 4 to the odd times x minus 2 to the even. And after you eventually multiply all of this out, we're going to have, well, x to the odd plus even. If that feels a little bit weird, then maybe like try it with some smaller numbers. We'll see some examples in a little bit here, but we can almost kind of imply our exponent rules here and say, okay, well, if this, like, let's do an example. Let's do maybe this is x plus 4 to the third power times x minus 2 to the second power. Or let's make it even easier because I don't want to foil too much. Let's make it where we just make this one the easiest odd. We'll make it to the first power. There we go. If we multiply all of this out, what are we going to get? Well, this is going to be x plus 4. And the next part is going to be x squared minus 4x plus 4 when we do all of our foiling. And then we would need to do some multiplication through again. And at the very end, we would have x cubed as our biggest term and a bunch of other stuff. And that makes sense because this odd number came from eventually multiplying this even number and the odd number here. So it's like we're adding the exponents. Okay, excellent. So the odd power seems to be nice and confirmable from any way you look at it, either from looking at the end behaviors, looking at how many things cross versus how many things touch, and comparing those exponents, adding them all together. Okay, but notice that all of our graphs, like we were looking at before, all of our reference graphs, they kind of started at the negative and then they went to the positive. And that makes sense because it was negatives to an odd power would make me negative, but this one is different. This one here has it starting the other way around. So it almost makes us think that it's that one of those graphs that was like what we started with, but we flipped it upside down. And so I'm thinking that that means like it was all of this stuff here, but maybe with a negative sign in front, so that we ended up having a negative of everything going on over here, which caused our entire graph to flip. Okay, so that's my theory. And as it turns out, each of these rules can be proven by just playing around in the same way that we did. So the end behavior here would help us to recognize it as an odd power, and we could say the leading coefficient is negative because that negative value is what's going to give us the similarities in our picture just kind of flipped over. Okay, well, what about this one right here? I have a couple different ways we can look at this. We have it where we, let's see, have one crossover, another crossover, a third crossover, and a fourth crossover. Okay, so we could look at that where this one's going to be some kind of even. This is an even exponent is going to cause that one, an even exponent is going to cause that one, and an even exponent is going to cause that one, and the last one. So if we think about this in terms of exponents, we're eventually going to have even plus even plus even plus even, which is just going to get us another even. Okay, that's one way we could think about this. A nice, simple way of employing our patterns. Another way we could look at it is we could look at it as the end behavior. Notice that over here it's going up to the positive, over here it's going up to the positive, and that only happens when I have an even power, just like in our reference graphs. So it's another reason for it to be even. And it looks like they're both going upwards, just like, our x squared or x to the fourth or anything else. So I could even say that our leading coefficient is going to be positive. So it's going to be even for our power and a positive leading coefficient. And it becomes as quick as that, where we can kind of recognize these common patterns, and it works out very, very well. Okay, excellent, excellent, excellent. Oh, did you notice that there's even one more pattern? Like, take a look at this one here. If we went back up to our references, again, if we kind of have one hump, then that was almost like I was going to have an even graph that goes along with it, one hump going with an even graph. But here, this x to the third was almost like I had one hump and then a second hump for my x to the third. And for the x to the fifth, I've got two humps that are kind of appearing here. Let's go down here and see what's happening. Here I had one hump and two humps, so I had an even number of humps. That got me a odd power. How interesting. And the next one I had one hump, two humps, three humps. I had an odd number of humps, and that got me an even power. So again, maybe there are some patterns that we're playing around with. Interesting, interesting. Okay, so explain how to find the x-intercepts called the real zeros of a polynomial function. Well, we've been doing that. That's exactly what we've been doing, is we've been trying to find the zeros. But this one here doesn't have multiplication happening yet. Keep in mind, the multiplication was really nice and helpful before because I just had to find out when one thing was 0, and it made everything into be zeros. Do we have a technique for taking something like this and making it into zeros? We do. We have it. It's called factor by grouping, and I'll do it two different ways just to remind us. One is I could do this in terms of a picture. I could try to look at this, and I could try to recognize some commonalities. Like, for example, maybe that x cubed and the minus x squared have some commonalities, so I'll put those together. And then I have the minus 4x and the plus 4 seem to have some commonalities. I'll put those together, and I could put all this into my rectangle diagram. Because in my rectangle diagram, I'm just going to be grabbing out those common sides. Like here, I could say that the common factor for x cubed and a negative x squared would be an x squared. And then over here, it would be this negative 4x, do we want to say? Or just, we could make a negative 4x. Sure, negative 4x not times x, because this other one doesn't have it, -4, just -4. And then we could say, okay, well, what are the things that need to go on top to make this true? Well, what times x squared gets me x cubed? That would be an x. What times x squared gets me a negative x squared? That'd be a -1. And I believe this is going to work out. -1 times -4 gets me +4, and x times -4 gets me 4x. Okay, so we can write this entire thing in its factored form as saying that it's equal to x minus 1 times x squared minus 4. But don't we recognize that this too can be written as a rectangle? Like, let's draw that in. This is going to be where I put my x squared at the top, and I'm going to put my -4. I'll put that down here at the bottom. And I'm trying to figure out what goes where. So that'd be x and x goes here. And then what times what gets me a -4? That'd be a -2 and a +2. But that means I would have to fill in these boxes because 2 times x would get me 2x. And x times -2 would get me -2x. Oh, but that works out just fine. Because sure enough, 2x and -2x is almost like I created something, but I also took it away. So sure enough, I could look at this entire thing as saying that it's equal to x minus 1 times x plus 2 from up here, and x minus 2 from the other side. So a really nice, quick way of factoring it. If this feels like you would prefer the symbol pushing, the symbolic manipulations, no problem. Let me show you how we would do that. We'd start again with our original one, f of x equals x cubed minus x squared minus 4x plus 4, and all we would be doing is our factor by grouping, which is the exact same thing we're doing in this diagram, but maybe we want to see it where we only have these variables. I don't know, I prefer more of the intuitive method, but I mean, you do you. So just like in our picture diagram, we pulled out this common -4, so let's do that over here. We'll pull out a common -4, and what's left is going to be x and a -1, and then we could factor the entire thing by pulling the common x minus 1 out, which again is what we did when we recognized that was a common side, and then we got x minus 1 groups of x squared minus 4, which again, maybe you recognize this as a difference of squares, this x squared minus 4, so that would be x minus 1 times x plus 2 x times x minus 2. All right, either way you want to get to this one, this is going to be something we want to get to quickly as this factored form, whether you do it with the pictures or whether you do it with the symbolic manipulation. But this is asking us about where our x-intercepts are, where our zeros are. And so we might need to draw ourselves a little bit of a sketch just to remind ourselves that if I have an x-intercept, it is going to be when my height is 0. I'm finding an x value that gets me a height of 0. So we could do another little bit here, a little model of logic, and say, okay, when does this entire thing get me 0? It's when I have x minus 1 times x plus 2 times x minus 2. Well, that's going to be pretty simple. We're looking then for when does x minus 1 equal 0, because if it equals 0, the whole thing equals 0, and same thing for x plus 2. And same thing for x minus 2. So it's going to be x equals 1, x equals minus 2, and x equals positive 2 for all of our zeros. So we could even plot those in, right? If we wanted to keep a sketch going just for our own reference, we could sketch that all in. X equals 1, x equals 2, x equals, oh, -2. Here you go, -2 right there. And so we'll put that in -2 right here. And could we actually have sketched this? Well, yeah, absolutely. In fact, it's going to be pretty easy. Notice that the exponents for all this situation, even though it's not written, these are all to the power of 1. And since they're all to the power of 1, that means they're all odd exponents, which means when I reach these zeros, I'm going to be crossing across my line. I just need to figure out what's going to happen at the far ends to maybe get me going. So let's do a few test points. Let's say what's going to happen at f of -10,000. Well, again, we can approximate that's going to be pretty close to saying that the first thing's just going to be -10,000 times the next thing, which is going to be about -10,000 times the next thing, which is going to be -10,000. And I think all in all, it's going to get me a negative number. So we would just say that this f of -10,000 is less than 0. And in fact, I don't even have to do any more than that because now I have enough to get all my pieces together. Since they're odd multiplicities, that means that I'm going to start with a graph down here. I'm going to cross at my -2. I'm going to have to cross when I get to the 1. I'm going to have to cross when I get to my 2. And it would make sense that my odd multiplicity would take me in the opposite direction as we go off towards positive x values. Awesome. We're really getting quite quick at this. Okay, I'm going to leave this one here for you. Have a you try at it. So let's, and in fact, I think I'm going to change this one There we are. I'll give you a different one. So we've got this f of x equals x to the fifth minus x to the fourth plus x minus 1. And I'd like you to try to think about what is this one going to look like. You can graph it out using the same ideas. Maybe think a little bit about what's going to happen if you were to put in some very large positive values, maybe some very large negative values. Maybe you want to factor this entire thing out using either the area models or using your factor by grouping with the symbols. But you're really going to want to try to find a way to find out where those zeros are. They're nice anchor points for controlling the discussion. Okay, so let's go down here and let's just kind of put some common language so that when we're working through our homework and when we're interfacing with other mathematicians or math students, that we can talk using the common language, something that helps to keep everything nice and clear, especially when we're learning online. So if x minus c is a factor of a polynomial function, then ooh, that's a lot. Okay, let's take this one step at a time. Well, I know that x is always my question, so let's put that in right here. This is my question. If I have question minus c, c is just going to be some number. So if I have x, if I have my x minus some number is a factor, and keep in mind that factor just means one of the things being multiplied. So we're going to say being multiplied, and of a polynomial function. So we can think of the polynomial function as just being this nice curve that's a fine kind of starting place for the discussion. So, okay, so if I have x minus a number is one of the things being multiplied in this nice curve, then, well, let's go back and let's take a look. So like when we did this one up here, and we had x minus 2, what did we know about this whole parenthesis? Well, when x was 2, I got a 0. Okay, so that would make sense then. Maybe that's what we're trying to get at here, is that if I have x minus c as a factor, then if I plug in c into my function, I got a 0. Okay, and that would make sense even if I had something like x plus c was a factor. I would be wanting to plug in what the negative version of it, which I could get back into this structure here. I just have to rewrite it a little bit. I'd be creative. X minus negative c would be the same thing. And sure enough, again, I would be saying that at this value right here is where we would be having our 0. We're just kind of grabbing it and stating that using some of our math symbology. Okay, so that's a nice way of saying it. If I have something minus something else being multiplied in, then when I can get that to be 0 by plugging in the right value, the whole thing becomes 0. Very nice. All right, if x minus c to the k is a factor of a polynomial, so now it's the exact same thing we had above. Now we've just got one of these kind of little binomials, one of these little parenthesis sets here, but it's just being raised to a power. So we're going to keep that in our mind. All right, so I have a situation to a power is a factor of a polynomial function where c is a real number. So real number just means what? I guess it's going to appear somewhere on my coordinate plane. That's good. And k is an integer. Integers, remember, are going to be those numbers that are positive or negative whole numbers. So those are going to be your negative ones, your zeros, your ones, your twos, etc. in both directions. Okay. Then what? Let's see. Is an integer such that k is greater than or equal to 1? Ooh, greater than or equal to 1. Never mind. So that's going to be not any of the negatives, positive exponents only. Okay, positive exponents then. Okay, so what this says is that if I have some, x minus a number thing being raised to a power, then that would be, if the power is odd, then what did we find out before? If the power is odd, what did we find? If the power was odd, wasn't that when we were crossing across the graph? I think so, yeah. And the evens when we weren't. So if k is odd, then the graph crosses the x-axis at whatever that c value was, at c, because when I plugged it in, that was my 0, and I know that for the odd numbers, that's what I'm about to cross. Okay, and the other one, then the graph, it didn't cross, we'll say it just touched. The graph touches the x-axis at c. All right, very nice. Love that. Okay, So let's see, find all the real zeros of this thing here. Ooh, look, it's factored. That's really nice for us. Determine the multiplicities of each zero, decide if it touches or crosses. Okay, and we'll try to get a rough sketch. Well, by now we've kind of made this really, really quick. This first one's going to be 0 when x is 0. That's a nice point. The next one is going to be 0 when, ooh, we could actually factor this one out, can't we? This could be written as x plus 1 and x minus 1. This is the difference of squares again. Those nice little tricks kind of help us out when we're looking at doing problems like this. So now I could write this even more factored out, where I have x times x plus 1 times x minus 1 times x minus 1. Okay. Well, that's actually, these are the same thing. So couldn't I write this as x times x plus 1 times x minus 1 to the second, and I could just talk about that in terms of all of this and its multiplicities now? Ooh, let's see. Okay, so this is the first 0 when x equals 0. No problem. X equals 0. The next one would be when x equals negative 1. And the next one would be when x equals positive 1 are all my zeros. These are my real zeros. Let's plot those in. X equals negative 1, x equals 0, x equals 1. Oh, this is going to be a nice, tight, curvy graph. Okay, let's see. Determine the multiplicities. Well, the multiplicity of this one here was just 1, I think, right? Multiplicity 1? Multiplicity 1, because I only had an exponent equal to 1. So that should be a place that I cross. Okay, we'll keep that in mind. So multiplicity 1. The next one was going to be also a multiplicity 1. So that's going to be a time when I cross. This one over here is a multiplicity 2. That's where we're just going to touch. And so let's go ahead and get some ideas here. Let's do some test points. Let's do f of, I don't know, a big number, negative 10,000. What's going to happen on that one? Well, we're going to have some kind of negative number for the first one. We're going to have negative times negative squared. So it's going to be negative times positive. So it's going to be a positive, I believe. So, okay, over here, we're going to be going somewhere up to the positive, and then we're going to, I think we should be able to sketch our graph, shouldn't we? I'm going up towards the positive. I know at my value of 2, or excuse me, at my value of negative 1, I have a multiplicity that's odd, so I'm going to cross over. I know at my 0 of x equals 0, I have a multiplicity that's odd, so I'm going to have to cross over again. And then I think on the next one, I have a multiplicity that's even, so I'm just going to touch and then ricochet on back. And this looks like it's something that starts in the positive direction, ends in the positive direction, and would normally correspond with an even power. And sure enough, up here, I have an x squared, and another x, such that if I multiplied all of these out, I would get something that is even. Do you want to see that? Let's just do that real quick for our own sanity. X times x squared minus 1 times x minus 1. If I multiply all this out, my leading degree should be an even number. So let's do this out. The first one would be x cubed minus x when I distribute there. This next one I could do in a rectangle diagram, right? I've got x cubed times or minus an x times an x minus 1. I could do this in a rectangle diagram and see x times x to the third gets me x to the fourth. X times negative x gets me a negative x squared. X cubed times negative 1 gets me a negative x cubed, and a negative x times a negative 1 gets me a positive x. So all in all, this should get me x to the fourth minus x cubed minus x squared plus x, and my leading degree is even, just like I figured it was going to be from the graph. And if all of that wasn't convincing enough, I did want to pull over the Geogebra just to kind of show, and here you can see again, this graph that we're playing around with looks very close to what we were thinking, where I've got this kind of dip and then this take back over. In fact, actually my sketch isn't too bad. If I kind of make it shade a little bit, you can see that it almost places right on top of that. It's going up on both sides. It's got a couple of dips, one place where it touches, and that's not a bad sketch for having only used a few points to help. All right. So now let's go ahead and take a look at here. This is going to be a practice problem that I'm going to leave for you. Let's go through and make sure that you've got everything you need. Is the degree of the polynomial function even or odd? Well, keep in mind you've got a bunch of different ways to do that. You've got where you can kind of try to count the humps and then maybe reason out from there. It looks like there's going to be about, like if there's 3 humps, then that's going to be a good chance that it's a 4th degree polynomial. but maybe that gets a little bit risky, especially if they're super flat or it's difficult to read. So we'll keep that one in our back pocket. Like I could look at this one really quickly and say as a quick rule that this looks like it has 1, 2, 3, 4 humps. So 4 humps is probably going to lead us into saying that is a 5th degree polynomial. So 4 humps is a 5th degree. But you try it from some of the other ways. Like maybe we touch in and say, okay, well, this one's going to be where it crosses, that's an odd. This is going to be where it crosses, that's an odd. This is where it touches, that's an even. And here's where it crosses, that's an odd. So it's like I've got an odd, an even, and an odd. If I add them all together, that should give me something that's odd. 5 looks pretty good for that. I've got something that has end behavior where I'm going up in one direction and down in the other direction, or vice versa. So that's also making me think that it's odd. Okay, so we got lots of ways to kind of double check ourselves and confirm. And if we forget one, we're going to remember the others and rederive them. Is leading coefficient positive or negative? So you're going to be looking to say, okay, what does it resemble? Does it resemble the normal odd, the kind of parent function odds that we had at the beginning of the packet? Or does it look like I might have flipped those upside down? If you flipped it upside down, that's a negative. All right, what is the value of the constant coefficient? That one's really interesting. What's the constant coefficient? In fact, we actually might have been able to add that into some of our stuff above, now that I'm thinking about it, the constant coefficient. Well, let's maybe come up with an example. Like let's do something like x to the 5th, and I wanted to put a constant on it, like x to the 5th plus 5. What does this mean? Well, we know from our transformations, this means I took my entire graph and I shifted it up 5. But we might also recognize that if I put in a 0 for x, I would get out an answer of 5. So this constant is actually, this is our y-intercept. So I should be able to say that this right here is our constant. It's essentially what happens if everything else multiplies out to zeros. I'm going to be left with just the number at the very end. Okay, so there you go. That would be our constant coefficient, would be a value of 2. Okay, so we did that one together. We'll put that in. And we'll write down some reasoning for it. So the value of the constant coefficient, we can say, since f of 0, when we put in a value of 0 for x, equals 2, then 2 is the constant. All right, do the real zeros and the multiplicity. Well, we went through that one. See if you need a rewind, you can go back and check a look at that. And then look at some of the possible functions that could represent this graph. Well, keep in mind some of the things that we're looking for. We're looking for things that are going to get us our constant value of 2 that has a multiplicity that's odd, possibly of degree 5. So we can go through these ones and check. Well, let's play around with some of these ones and disqualify them out or qualify them. So we're looking for zeros that are at -5, -2, 1, and 4. Okay, well, here's our one for -5, here's our one for -2, here's our one for 1, and here's our one for 4. That one looks like it checks out. And I think that's going to repeat here, and I think it repeats here, and I think it repeats here. Okay, so nothing gained there, but still, a little bit of use. What do we have as far as the even and the oddness? Well, the first one should have been odd, the next one should have been odd, the third one should have been even, and the last one should have been odd. So we got odd, odd, even, odd. Here we go. To the first power is odd, odd, even, odd. That one looks pretty good. This one here, odd. Nope, doesn't work. That one should be odd. So that's going to be a disqualifier. The next one, odd, odd, even, odd. That one looks pretty good. And then the last one, odd, odd, even, odd. That one looks pretty good too. Okay, so we disqualified one of them. Oh, what else do we need? Well, maybe I want to think about how all of this is going to multiply out, and am I going to get that constant? Now, we've been playing around a lot with looking at how those leading terms, like these x's, you can kind of already imagine in your head that if you multiplied all of these out, you'd have your x's, and every time you multiply by another x, you'd get a bigger power and a bigger power. But similarly, the numbers at the end here are going to multiply to just get us bigger numbers and bigger numbers with no x's. So actually, we can think about how this would all multiply out. This is almost like at the very end of multiplying all this, I would have multiplied a 5 times a 2 times a -1, but there's actually 2 of those -1s in there, so I would have multiplied it by -1 twice, and then I multiplied that by a -4, and that's going to be the number that's at the very end of all this multiplying. If that feels weird, let's take a look up here. Remember this one right here we were looking at, we said, okay, like if I was going to actually multiply all this out, it'd be like I had an x in the front, and then I had this -1, would have to multiply by the -1, get us the +1, and sure enough, like you can see that that's exactly what happened over here with that x value rippling on through. Okay. In fact, actually, that's an interesting way of thinking about it too. We could have looked at this entire thing as where, instead of having it as x times x plus 1 and x minus 1, and we could have thought of this as x minus 0 times x plus 1 times x minus 1 times x minus 1. And then it would have made a lot of sense why our constant term was 0, because this 0 was going to multiply through to cancel away with that one, and multiply with that one, and multiply with that one after we did our full distribution. So it's like I had a constant term of 0 by just multiplying those numbers at the ends of the binomials. Okay, so then down here, what has that taught us? We have 5 times 2 times -1 squared, so -1 times -1 times a -4 would get us what? 5 times 2 is 10, times a -1 times -1 gets us still 10, times a -4 gets us a -40. Oh, but this is being multiplied by a -1 over 20 in the front, so -1 over 20 would have been the same thing as having this over -20. And I think that would have gotten us a +2. That one seems pretty good. That one seems like it's checking out. What about down here? Would it have worked with this one as well? I don't think so, because notice that the only thing that's different is that in the front, there's not a negative sign. And we can kind of recognize that even though this one looks like an odd function, it's a function that's starting in the wrong way. So we can actually determine that the leading coefficient should have been negative. So again, this one's looking better and better. This one is disqualified because the 1/20th in the front is a positive number, and a positive would make it look like that S shape. And this one looks like kind of the flip of that S shape. So, okay, 3 is disqualified. And would number 4 work? Number 4 looks like it has all the pieces, but I don't think that the number in front is going to work out to get us the constant term of 2 that we need. So I think that we get our answer of saying I is the correct graph here, or one of the possible functions that could be represented here. I mean, after all, because we haven't done anything in between the -5 and the -2, because we haven't actually plotted all of these points, we don't know that the graph isn't doing something crazy like this, and doing something kind of ripply in between here and up here. Like, all we know is that, oh, I guess it would have still needed to cross through the intercept there, so it would have maybe dipped back up and then touched, and then like there's a lot of things it could be doing that we're not fully sure on. So that's why we just call this a sketch. We've got a pretty good idea of what it's happening, and we're just having to kind of settle with the fact that we don't know for sure, but we know enough to get a decent idea. Okay, let's clean this up so we don't confuse ourselves when we look back at the notes later for studying. And that's all that we have. So the idea here of the graphs is just, again, these are like logic puzzles. How do the powers interact? What's all the foiling that's going to be happening in our brains, or what's all the distribution that's going to be happening in our brains? What the polynomials look like? Are we going to be needing to include any of these ideas or not? Things to play with, but they're all things that you already have the tools to be using. So enjoy this, go back, think on it, let me know if you have any questions, and I'll be around to help.